In this section, we're going to discuss case study involving a stack abstract data type. Stack is an abstract data type, which means that it defines a data structure based on its behavior and characteristics rather than anything dealing with implementation. How we implement a stack could be done in various ways. That is not defined in the stack concept itself. Here with the stack, we define two different methods that must exist on it. The stack is known by these two methods. The first is called push. That's where we add a data element to the stack. We can push multiple elements. If we were to push the values 1, 2, 3, we would push 1, push 2, push 3, and they would be contained in that data structure in that order. Pop is a different method that does the exact opposite. It removes elements from the stack. The stack has the concept of a top. Conceptually, think of it as a tube into which we push things, and to retrieve them, we tilt the tube and they pour out one at a time. This data structure is known as a LIFO, L-I-F-O, last in, first out. If we were to push the values 1, 2, 3, we would pop them in reverse. We would pop 3, 2, 1. The 3 went in last, it comes out first. The 1 went in first, it comes out last. By contrast, there's an abstract data type called a queue. If we were to push, technically add, 3 elements, 1, 2, 3, to the queue, we would retrieve them in order, but starting with the first. We would retrieve them 1, 2, 3. Assuming an empty stack, meaning no elements pushed on it, a push operation adds an element to the top. This element is available to be peaked if the peak behavior is defined, or pop. That means we push it on, we can easily pop it off. When a second data element is pushed onto the stack, the first one is obscured. It is pushed down in the stack, it becomes unavailable. We can't touch it. The second element pushed on is the only element available. The only way to get back to that first element is to pop the second one and allow the first one to come back to the top of the stack, from which we could then pop it. Usually stacks have helper methods. They're not required for the behavior of a stack, but they're often helpful. The peak method mentioned before allows program to look at the value of the top element of the stack, but it does not pop the element off. It remains at the top of the stack. Generally, it's good to know whether or not your stack is empty. Many stack implementations define an isEmpty method. It returns true if there are 0 elements on the stack, false otherwise. Based on how a stack is actually implemented, it may prove beneficial to have an isFull method to know that the stack can no longer receive any pushed elements. If this method is not available, chances are good the code will throw an exception when pushing an element that exceeds the capacity of the implementation. Another alternative, which is even better, is to grow the capacity of the stack to allow the additional pushes. Many problems benefit from the last in, first out behavior stacks. We discussed recursion before, where a method will call itself, and each time it calls itself, it has a copy of the parameters, local variables, etc. The stack mechanism is used by the machine to remember all of those. Each time the recursive method is called, a new stack frame is created. It pushes all the values onto it, and the method proceeds to execute. When returning, we have a record of which method called which, and in what order. And we just pop those stack frames off of the stack and obtain values and continue execution from that point.